Hi, I am Nakık Aksaç, and this is our Wearable Health Observer project. This is our content. Firstly, we prefer to select the most suitable sensor for our health monitor. The compatibility with our design and the accuracy of the data were our top priorities and choosing appropriate sensor. We adjust the sensor settings and conducted the simple measurement on the top of the watch to test our observations. Based on the test we conducted, we observed that our probe temperature sensor and analog heart sensor were not suitable for our project. The probe sensor provides average outputs which provide inadequate for surface area measurements. The analog heart sensor, on the other hand, failed to generate reliable data within the circuit powered by the battery. The reason for this was the power loss in the electrical signal caused by our battery charging circuit, which gradually increased the margin of error in analog measurements. Therefore, we decided to use our new sensor capable of measuring red and infrared light reflections. For the step sensor, we utilized a better regulated sensor to improve the clean lines of our data. With our sensor that measures red light and infrared light refractions, we were able to obtain temperature readings through the infrared measurements. Additionally, by comparing the refractions of red light and infrared light, we can detect the instant decreases and increases in our oxygen levels. When our sensor takes a measurement from fixed position, we can identify blood pressure increases and decreases when visualizing the data on graph. For heart rate detection, we can easily detect it using both infrared and red light, and by balancing it with our data transmission rate. We can determine our heart rate per minute. We chose 15 seconds measurements to improve the accuracy from medical perspective and avoid making system visuals appear unappealing due to frequent updates. When integrating our MPU sensor, we opted for an improved MPU sensor that is more suitable and well digitalized rather than using conventional MPUs. This choice required us to include certain additional components in our functions. But the speed and accuracy of the data we obtained were much more satisfactory to us. Due to limited space and insufficient printing technologies, we choose local printing for PCB fabrication. By utilizing I2S communication protocols in our sensor, we ensured that the data exchange lines of the sensor were provided through the same line, thus avoiding circuit complexity. We had to work with small soldering for assembling our electronic board and components. First, we soldered PICO followed by our motion sensor. We facilitated placement by creating new line for charging our circuit, enabling the freedom of movement for the charging circuit. Finally, we placed our heart sensor and prepared our circuit for display connection. Once our circuit was completed, we securely attached it to our watch, aligning it with the position where the heart sensor would be. Initially, there were some challenges in terms of communications and reprogramming when it came to the display cover. We thoroughly tested our code, reset the circuit for a fresh start, and then integrated the battery into the circuit to facilitate remote data exchange. With the built-in Wi-Fi system in our circuit, we established a system that will transfer data every 50 seconds during each heart measurement, ensuring ease of use for our microcontroller and watch. We transferred the data we collected every 15 seconds to both our mobile and web application as JSON files. Through the cloud system, we create real-time data monitoring is possible without the need for data storage. We initially defined our 16-bit display driver and screen bits to our microcontroller and prepared manipulation functions. We implemented the real-time step increment and handled the change in the screen data. However, this caused some difficulties in refreshing our screen layout. To maintain the speed of our microcontroller, we sent the step count and heart rate measurements to our screen every 5 seconds. During our work, although we initially used small and easily integrable batteries, we eventually integrated a slightly larger battery into our circuit, allowing for usage time of 25 hours in terms of size. As you see on the left screen, we sending our data through our main file. And you may see our app database right side of screen. After every 5 seconds, our screen layout refreshed and our data is refreshed.
Hi, I am Onurcan Bilekyiğit. Our mechanical design was done within the limitations of sensors, batteries, PCB layouts, and screens. We aimed to create a compact structure to ensure usability. Throughout this process, we made changes to the mechanical design due to sensor and battery replacements. To address weight issues, we transitioned our material from aluminum to filament, which led us to utilize a 3D printer for production. In this context, the produced prototype of the watch is displayed, featuring its assembled state alongside its accompanying components. It should be noted that while further reductions in size were conceivable, it was considered uneconomical due to the escalating costs associated with downsizing individual components. In conclusion, we strived to minimize the dimensions while adhering to practical limitations, achieving the extent of miniaturizations displayed. In this excerpt from our code snippet, you can observe the data acquisition process from the accelerometer, pulse sensor, and temperature sensor. Here you can observe our effort to convert the obtained acceleration data into step count. By comparing peak points and in the acceleration data, we transform it into a step count, which will be utilized in the future for activity recognition purposes. To prevent continuous memory allocations within our system, we retain 3 sets of data for comparison, subsequently overwriting the oldest set with the next data point. In the given context, our focus lies on the extraction of pulse data through the considerations of peak values. However, due to the proximity of these values, the unintentional inclusion of extraneous data poses a potential challenge during the counting procedure. To further refine data optimizations, we have introduced the implementation of +1 criteria. This criteria serves the purpose of excluding specific values that are deemed irrelevant and should be disregarded within the counting process. By integrating the +1 criterions, we aim to augment the efficiency of our data analysis by ensuring the exclusion of superfluous data points and fostering a more accurate representation of the desired pulse data. Activity classifications has been conducted by analyzing the step count within 15-second durations. This approach allows us to capture the frequency and intensity of physical movements within a short interval. By examining the step count data within this time frame, we gain insights into an individual's activity level and patterns. Using predefined thresholds or machine learning algorithms, we can classify activities such as walking, running, jogging on the step count values. This classification process provides context-aware activity monitoring and analysis.
For software architecture, we will develop a collector software that will collect real-time data. This data will be transferred to database, and through a trainer software, we train and obtain our model to use with real-time datasets. With the real-time data analyzer software, using real-time data and train model, we analyze the data and show results through our GUI. Here you can see our process flowchart. We did exploratory data analysis to understand characteristics of our data. We used pandas, numpy, matplotlib, scikit-learn. We used two different perplexity number, and higher perplexity resulted in better classification results. But as shown in the figures, blue and red dots present sitting and standing, and we had lower accuracy for them. We choose LSTM model. LSTM stands for long short-term memory. LSTM is a type of recurrent neural network designed to handle a sequential data, like time series. LSTM was developed to prevent vanishing gradient problem that is a common problem in traditional RNNs. As shown in the first figure, we obtained model training results. Model loss and accuracy values are stabilized around the values where accuracy is 0.91. As shown in the second figure, we plot loss and accuracy values through training. As shown in the third figure, we plot the confusion metrics to see our model performance for recognizing these three activities. As we predicted at the end of the exploratory data analysis, our model confused between sitting and standing and makes more false classifications with sitting and standing. With datasets, we train our model. At first, we tried 8 hidden layers and obtained figure 1. We failed with 8 hidden layers, and then we tried 32 hidden layers and we obtained 0.94 accuracy. We use Bubble.io to build Who Watch application. User and health professional can sign up and create their profile via Who Watch app. Who Watch app contains a database where we store sensor data that we collected through our Wearable Health Observer smartwatch. We use communication protocol while transferring the data that we collected with Wearable Health Observer smartwatch. After that, we use Bubble Data API plugin to transfer data To our Who Watch application database, we create the data type name user activities that has fields contain information about users' daily activities and general health conditions like heart rate, temperature, and steps. For the standalone application, we use JustNet, Wearable, and Android Studio. First, we obtain our app and emulate it in the Android Studio environment, and then download our application to our phone. Here is a clip of how our application works. We successfully obtained targeted outputs. Total budget spent for this project is 4,570 Turkish liras. Conclusions. Electrical, mechanical, and software architecture are completed. Mechanical analysis and electrical simulation are done. Human activity recognition algorithms are developed and aim accuracy is obtained. Web and standalone applications are built. We create a database for further research. Produce first prototype. We thank you for listening.